let's do it. So, we love np.random.choice. That function from the NumPy library was very simple, but it gave us so much power. We got to simulate stuff with it. All it takes is it takes a sequence. That's what it's required to take. It takes your array of things and it just picks something randomly out of it. That's the most basic way to use it, right? But you could also use it with an extra argument, and you could say, I would like you to pick randomly this many things from the array. N things. Like I want 3 things. So just randomly pick things that many times. So we did that with like flipping coins, right? np.random choice with my coin array that had heads and tails in it, and it gave me 42 heads and tails. And I could count that. I did some really cool function-based stuff that all led into simulations, right? So that was beautiful. We talked about gambling, and that was the end of it last time. So let's pick back up there. We also learned about like if statements, if else, bunch of trying options, and yeah, we learned about loops for something in something else. You're going through a sequence, or iterating through a sequence, and visiting every item in that sequence, doing fun stuff. And yeah, that just led into simulations. And the last thing that we did to build this beautiful graph, let me remind us, was this graph was generated by coming up with an experiment where we're like, I'm going to flip 100 coins, and I'm going to count how many heads were on those 100 coins. And you know that if you do that, not every time is it exactly 50. Like you expect to see 50 because it's like a perfect fair coin, right? But sometimes it's more, sometimes it's less. So like you just do this kind of thing with counting on 0 equals heads, and it gave us back the number of heads for those coins. And we turned that into a function where we flipped 100 coins, counted the heads on those. So here were our 100 coin flips. Here were how many heads there were, and we returned that number. And every time you call it, it gave a different value back. And then what we did is we played that game, that experiment of flipping 100 coins and counting heads. We did it 20,000 times. And it just happened within a second, because the computer's so fast. And we just had a size 20,000 array of a bunch of counts for heads after flipping random coins 100 times. And these numbers are close to 50, but they're never exact. And we turn that into a table, and we did a histogram because we have a numerical distribution. We wanted to see the distribution of those heads values, and you can see that it is centered around 50. It's most likely that when we did the simulation, we saw 50 heads. That one had the most, that was the most numerous bit of options. But then you can see that there's a bit of a tails on both sides, where like sometimes when you flip 100 coins, you get like 60 heads. You got lucky, but it's totally within the realm of possibility. Same with like getting only 40 heads. You got more tails that time. It's less likely, but it's still possible, right? You know that if you flipped coins for like the entire amount of time the universe has existed, you will eventually get 100 heads in a row. Eventually. Didn't happen in our data set, most likely, in our simulation. But if you did it, like, it is possible, right? It's like the chances are so small. It's like 1 over 2 to the 100, which is a microscopic number. It's so unlikely, but it is possible to randomly flip a coin and get 100 heads. It's just like the distribution of that is going to be so small. Okay, does that make sense? So that's what we learned how to figure out. And taking that average, we see that it is centered around 50. That was beautiful. Are there any questions about that before I have you try something? All right. So, yeah, I want to ask you a question about, let's see, about one of our data sets. I'd like you to play this game for the Titanic data set, please. I'll include it, and then we'll get started. I'll help you get started. But I want to turn this into a few questions. Like this will be step 1, just first bullet. And we'll come back and we'll turn this into step 2, and maybe we'll do the histogram together. But what I'd like you to try with me is break out that Titanic passengers data set, and I'd like you to make a group of 100 of them randomly. I'd like you to pick 100 random Titanic passengers, and let's see, yeah, 100 random Titanic passengers, and I'd like you to count how many of those random passengers died. All right, so let's talk about how to do that before I let you go off and try it. But let me read in that table. Boop, just like that. There's Titanic. And remember, you can do np.random.choice on columns of a table. Where was my roulette example? Here it was. See this here? This is essentially what you'll be doing right now. All right, so np.randomChoice on a column of a table. That's kind of what you're about to do. All right, so that's a piece of it. And do you see how for the Titanic data set, if you did the survived column, you get a bunch of ones and zeros for who survived, right? So you're going to randomly pick from that column. Does that make sense? Randomly pick 100 people from that column and try to count how many died. So that's also going to be similar to this idea of counting heads. So this was randomly flipping coins and counting heads. So I guess, now let me bring that back to, let's take the full function. So those two ideas, like that one and this one, taken together, give us kind of what we need for this first part. I'm really just trying to get you to do this middle bit right here where we do the counting. But try to take 100 Titanic passengers and count how many died. All right? By getting that column, that survived column out of the table. We can do some equals stuff to figure out what was happening there. But remember that died is 0. And so if you did count non-zero after you took 100 random people from that survived column, it would tell you how many survived, not how many died. So you have to like turn that on its head somehow. You see the idea there? So give that a try, maybe a few minutes, and then I'll show you my answer. And then I want to do a simulation here. Even though we know what happened in the Titanic, it's still fun to play around. Let's do that. I need to do that too. So go and get that survived column. Let's see. I need to respond to both of those. Okay. Who's that? Oh, that's right. Do we figure it out? How to get the number of people who died rather than just survived? Let me try. So let's see. Trying to do it like this, like the outcomes or the number of non-survivors, unfortunately, this time. So let's see. It's the survived column for sure. So I want to go into the Titanic, dot column survived, bunch of ones and zeros, and I want to get a bunch of those, right? Oops. And np.random.choice on all that. And this just gives me one element of that, but I want 100. See how that's going to give me 100 random passengers from the Titanic, ones and zeros, and whether or not they survived. So those are like my outcomes, going back to this example. Those are like lived or died. And if I were to do this, np.count non-zero, because they are ones and zeros, right, of outcomes, they would count the ones, and one meant survivors, right? So in my random sample this time, I got 38 survivors, but I want to count the non-survivors. So if I got 100 guys here, I can do 100 minus that to get the other side of that, right? Count the zeros, pretty much. Does that make sense? That will give me 100 people randomly from the Titanic and give me back how many did not survive. Questions about that? Because now we can do some fun stuff. I would like us to next try to turn that into a function that gives back that count every time I call it. So something like this, like make a function called sample 100 passengers and count how many died, something like that. So do that, and then I'd like you to run it 2,000 times and see how many survivors you get. How many non-survivors you get. So that's going to end up looking a whole lot like, this, where I did this with 20,000 repetitions. And I made an array. I want you to do something similar, but with 2,000 repetitions. All right. So does that make sense? Try to make a function that does what we just did, and then run it 2,000 times, keeping track of all the non-survivor counts, I guess you can call it that. So use that pattern, please. And let me know if you have questions, but I'll do this after a couple minutes. I'll give you a head start. If you do it fast enough, try to get a histogram going there. You can go to our code from class to see it in action. But that's a good start, I think. During this time, I can respond to this question. Shoot. I guess I'll have to do that next time. That was the loudest thing ever. Let me mark something as unread so I don't mess with it. That one. And let's talk about it. Did we get it? Did we make a function that made it work? First of all, what should be its long giant name like I had here? I think what I chose was something like sample 100 passengers. So I want to turn this into a function that just like kind of gives that back every time I call it. This a new sampling of people. Sample 100 passengers and count the dead ones, unfortunately. So I just kind of want to copy and paste this, really. It's just, I want to do this work every time I ask for it, and I want to give it a name, rather than just like copying and pasting it. And the answer, to give it back, you say return. So that's the only difference. Right, so now I can call it as much as I want. Sample 100 passengers and count dead. Every time I run it, 66 dead passengers in this sample, 54 in that sample, 58 in that sample. So it's random, but it will probably, on average, approach the actual number of people who did not survive the Titanic. All right. So does the function way make enough sense so far? Are we ready to do it 2,000 times, calling it, keeping track of things? Let's do it. So something just like this, right? I want to make a bunch of counts for not heads, but like non-survivors. Non-survivor counts is like make an empty array and just like do it a couple thousand times. So for I and np.a range 2000. So this is going to be it's going to let I go from 0 to 1999, but it doesn't matter. I'm not going to use I just want to run the body of this loop 2000 times. I want to get a new, just like I was doing here, instead of head count, it's like I can call my function, I want like a non-survivor count. So it's this, but singular. Sample, like call it, give me that value back, and then add it to non-survivor count. So I want to append to it, it's np.append to non-survivor counts this new value that I got here. And then np.append does not change anything. So if I want this to be still, like I want non-survivor counts to get bigger, I have to assign it back into it. And so if I do that 2,000 times, now I have 2,000 elements in my non-survivor counts array. 2,000 non-survivor counts, unfortunately. It really did get filled up with 2,000 things. And just quickly, we could do a histogram, right? We can turn this into a histogram by putting these non-survivor counts into a table. Right? Make a blank table with a column for non-survivor. If I can spell survivor counts, and then put them there. Now it'll give me a table with all of them. And if I do a histogram on that table, it's just the first and one and only column 0. I can say, I get this little histogram. And you can change how many bins you want. Just like by default, it makes 10. You can say, I want 15 bins, please. And it looks like through this sampling method, I get around, I don't know, 64-ish usually non-survivors. But sometimes we get lucky. There's not a lot of non-survivors. Sometimes we get really unlucky in our samples. There's quite a lot of non-survivors. Are there any questions about how we generated this graph and how we created this? A little morbid, but you better believe probably that this bin right here, whatever it was, like 64-ish, 63-ish, I don't know, something around that, or even here, like they're kind of fighting for each other randomly. One could have been bigger than the other. Around there, in between like 60 and 65 is probably the true number, like the true percentage of non-survivors on the Titanic. And you can totally check for that, right? You can go to Titanic. We have the survived column. You can ask, here's all the survivors and non-survivors. You can count non-zero that, right? NP dot count non-zero. So here's the number of Titanic survivors, 342. You can divide by the length, how many people were on the Titanic, like length of that column, maybe. That's the quick way to do it. Or like the number of rows in the table, either way. So that's the percentage of survivors. If I do a subtraction, 1 minus that, this will give me the percentage of non-survivors on the full Titanic. And it looks like it's about 62%, and that makes sense. These bars are pretty high around there. It's going to, randomly, it's going to choose in that 100-sized sample, it's going to choose usually as the same kind of ratio of people who really didn't survive. That's kind of interesting that it's gonna notice that in the long run. Any questions about this example? See it all coming together? It's just like the heads and tails stuff, just with a different flavor. If we're good, I want to talk about probability, because I mean we hinted at it. You can't get away from it in data science. Let's talk about probabilities. Like we just made one, so 62%. Like you know probability, but let's say the words and remember all this and try to do it in code too. So, all right, probabilities in general. You know that probabilities for events that may happen, things that might happen, is either a 0% chance or a 100% chance. You can't have like 200% chance that something happens. That doesn't make sense. You can have a negative probability either. So the lowest probability value for something is 0. It means that this thing that you're measuring, its probability is impossible. It never happens at all. So probability values are between 0 and 1, but sometimes we multiply that by 100 and stick a percent sign at the end. So like 0% to 100%, right? It comes from the Latin root of 100. But really, when we're calculating values, it's between 0 and 1. That's what a lot of the libraries care about. So the highest value for a percentage, or for a probability then, is 1, which means that this thing you're measuring is always happening. It's never going to not happen. Perfectly always happening. So 100% is a way of saying that. It's the chance that something is going to happen. And that's something we usually call, in probability theory, we say events. Event is this thing you're trying to measure its probability of. So there's that. You can do a complement. That kind of makes sense. We actually just did a complement. This is before this 1 minus stuff, this was the survivor percentage. And I did 1 minus it to get the non-survivor percentage, because that was the opposite. So the complement is the fancy word for opposite in this sense. So if an event has probability like 70%, 0.7, then the chance that that event with probability 0.7 didn't happen was, well, it's what's left over. It's 1 minus 0.7. So it's 30% chance that it didn't happen. Does that make sense? So, yeah, a good thing to figure out probability, like the first thing that we learned about is like rolling dice. So like, what's the probability that your die lands on like a 6 or something, the highest number? Well, it's 1 over how many sides there are. So like 1 over 6 was that, and so that's 17-ish%, right? You see how I'm reading that? 17-ish% for that one. So that's probabilities in a nutshell. I think you've probably seen all this, or at least read about it by now in the book. Let's talk notation. So the idea of all your options, the things that may happen when you're like figuring out probabilities, they're called outcomes. So the outcomes for rolling a die are 1 through 6, right? Those are your outcomes. You can't roll a 2.5. You can only roll a 1, 2, 3, 4, 5, and 6 on like a 6-sided die. And so those are all of your outcomes. And we can ask for the probability of each of those, right? It's always a 6th. So, yeah, that's how that works. The probability of anything, some event, some variable idea of an event A, the probability of an event A happening if every outcome is equally likely, like it is for flipping a fair coin or rolling a fair die, we say P for probability. The probability of event A is, well, the number of outcomes where A is happening over the total number of outcomes, because it's always the same likelihood for each one of them. All right. So for a fair die that's 6-sided, what's the probability of like rolling a 1? You'd say P of 1 kind of. What's the probability of getting a 1 on that die? It's 1 over 6 or 17-ish%. You can also ask the question of like, what's the probability that I get an even number? So it's the probability that I see an even number on my die when I roll it. Well, what are the number of outcomes that make that happen for a 6-sided die? It's 2, 4, and 6, right? over how many total outcomes are there on rolling a die? 6. So it's 3 over 6. So that simplifies to a half, of course, but there's a 3 over 6 or 50% chance, right, that you see an even number when you roll your dice. Whereas for each possible outcome, it's just like a 1/6 chance. So there's my best drawing of a die. Cool. Does that make enough sense? Questions about those terms? Maybe we've heard them before. So yeah, usually a lot of the things that we talk about, like it's the everything is like equally likely, truly random. It's not like a loaded coin where it's sometimes it lands on heads more often. It's perfectly fair. All right. So are we ready to have an interesting probability game to learn about? All right, just yell at me if you have questions. So here's a fun idea. This is a silly game. I think it legitimately came from a game show, but it's in every probability theory textbook nowadays because it's going to show us something about probability that is very, very non-intuitive. It's going to be a little weird what we're about to learn, but I'll try to make it as intuitive as possible. All right. So it's a game. It's called the Monty Hall Problem, and it's modeled on like an old '60s game show. And here's what it was like on this game show. So like the host's name was Monty Hall, and the contestants would come in and they'd be presented with 3 doors. All right. So imagine that you're a contestant on the Monty Hall game. There's 3 doors, and you want to win the car because there's a car behind one of those doors, right? And you get to pick eventually. There's a car behind the doors, and then there's things that you don't want behind the other doors. People use goats as an example. So there's goats behind each of like 2 of the doors and a car behind one of the doors, and you're not sure which one. All right. So you get to pick a door. You may see a goat or a car there. Okay. More likely it was a goat. So let's play the Monty Hall game a couple times, and like we will do it randomly. I will pick a random number. I'll ask Google to pick a random number between, or I'll do np.random.choice between 1 and 3. And then the way the game gets played, by the way, is you the contestant, pick a door, and then what Monty does, the Monty Hall person, the announcer, he's going to open, like let's say you pick, I don't know, let's say you pick door 2, and that really was the car. He's going to say, all right, Monty Hall is going to open one of the doors that you didn't pick, and he's going to show you one of the goats. All right, it's going to be like, all right, I'm going to open this door for you. You pick number 2. I'm going to open up door 3. I'm going to tell you that there is a goat behind door number 3. And so now it's between the one you picked, number 2, or number 1, right? You're not sure which one has the car. He's going to ask you next, do you want to keep your choice of door number 2, or do you want to switch to the other one that I didn't open for you? All right. This is the probability game. It's going to be a little unintuitive, but that's your choice. And you can either say, I want to stay with the door I picked originally, or I want to switch to door number 1, the other one that wasn't open still. And then he lets you open up the one you chose. You have the choice of switching though. All right. And so does that game make sense? It's a little weird, but let's play it to see what happens. It's going to be a little unintuitive. All right. So here's the game. I'm going to pick a random number between 1 and 3, but here are your 3 doors. I'm going to pick the door that the car is behind. And let's see, who wants to play? Would you like to pick a door? You're going to pick door number 2. All right. I'm going to figure out which door the car is behind, or the goat and the goats as well. I'm going to open up door number 1 and show you that there is a goat behind door number 1. Do you want to open up your door number 2, or do you want to switch to door number 3? 3. You want to switch to door number 3? You unfortunately lost the game because the goat's behind that door as well. You were right the first time. Oh man, so that was your original guess. Okay, another time. Whee. One of you guys, pick a door, please. 1, 2, or 3? 3? All right. You picked 3. I'm going to open up door number 1 again. And I'm going to say there's a goat behind door number 1. Would you like to switch to door number 2 or keep your door number 3 guess? You keep it? All right. Let's see here. Dun, dun, dun. Unfortunately, it was behind door number 2. Darn. So this was also a goat, but the car was behind door number 2. Let's do it one more time. Can you win? Do you see the game? All right, let's do it this way. All right, one other person I haven't heard from. Pick a door. 1, 2, or 3. Play the game.
3.
You're gonna pick 3. All right. I'm going to open up this time door number 2 and show you that there is a goat behind door number 2. Would you like to switch to door number 1 or would you like to keep your door number 3 guess? You're gonna keep it. I am so sorry you lost the game. The car was really behind door number 1. So it seems like we switched sometimes. We kept it another time. We were just really unlucky this go round. I'm sorry, but let's figure this out. It's actually going to make more sense. It's actually going to be correct to always want to switch your guess. It's going to be twice as likely that you get the car if you switch your guess. And let me show you that. All right. It's a really weird idea, but I'm gonna prove it to you. All right. And then I've made a simulation for it. So let's see. Do I want to show you the simulation first, or tell you the idea first? Yeah, let me show you the idea first. So here's kind of we're gonna do a simulation to prove this. We're gonna make a simulated game of the Monty Hall program, but you should always switch. Actually, we were just really unlucky this go around, and you should always switch. But and here's why. So let's say that you guess door number 1. All right, and then Monty opens up the one with another goat, or picks a random goat if you picked the door with a car. So he opens up like door number 3, and the question is like, how often do you get it right the first time? How often did you do it right the first time and pick the door with the car? It's a 1 in 3 chance, right? If it's perfectly random. There's a 1 in 3 chance the first round you guess the car, and if you stay with your choice, you keep that 1/3 chance. Does that make sense? If you stayed with your choice, you kept that 1/3 chance, you did not let anything else happen, you had a 1/3 chance of getting it right the first time, and you stayed like that. The door being open did nothing for you, okay? If you switch, what has happened is there used to be 2 doors, right, that weren't open, but one of them is open now, right? There used to be 2 doors that weren't opened, and they had a 2/3 chance then of having the car. Does that make sense? The doors that you did not open, the 2 ones that you didn't pick, there's a 2/3 chance, because yours is 1/3. The 2/3 chance that it's behind one of these doors, right? And when Monty opens one of the doors, the whole 2/3 chance of the car moved to here. Does that make sense? So that's what happens. And so if you switch then, that 2/3 chance, it kind of collapses into that one door. And so you are more likely, we just got really, really unlucky this go around, sorry, of winning the car if you switch, okay? If you switch, you get the car, and let's prove that. So let's make a simulation for the Monty Hall game. All right. Boop. I have some code that I just want to paste in. You don't have to understand it fully. Or you can look at it later. I don't want to type it, I guess is what I want to say. Here's a giant function that simulates you playing the Monty Hall game. So here it is. Let me run it once. This is simulating the Monty Hall game. What it's going to do is it's going to give back a sequence, not as an array, but with like square brackets. It's called a list in Python. It's pretty much an array. It's going to give you back like your original guess. We're going to randomly pick a guess as well. The door that Monty Hall gives you back, he shows to you, and then the door that you could switch to. Okay, so that's going to be how we simulate this game. All right. So we're going to make a guess randomly of our doors. Here's the doors. Our guess is either the door with a goat, the door with the other goat or the car, right? So we're going to guess one of those, and randomly, right? We're going to randomly pick one of the doors, and it either has a goat or a car, and so we'll get that guess. That's our random guess. And then if we guessed a goat, then our original guess was a goat. Monty's going to show us the other goat, and we'll get a car in the door that we could switch to, right? If we pick the other goat, same idea. It's just goat 2 versus goat 1. Otherwise, we pick the door with a car, and the first time, and so we have 2 goats to choose from that Monty could show us. We will shuffle them. There's np.random.shuffle to jumble which goat Monty's going to show to us. So car, you could either show us goat 1 or goat 2, and then the one that we could switch to is also goat 1 or goat 2. All right, so that's our simulation of the game. Our original guess, what Monty shows to us, and the door that we could switch to. Okay, and so we're gonna try to simulate what would happen if we stayed with our original guess. We're just randomly showing this, right? And what would happen if we switched to the other guess? This time, if we switched, we would have got to go, unfortunately. We should have stayed with our original guess. I'm going to show you that only happens a third of the time. It's twice as likely for you to get it right if you switch, okay? So let's play the game a few times. I'm going to make a... oh, this is disgusting. All right, I want to copy and paste that again. Boop. Okay. This is going to be really odd. Here I am making a table that's blank, but it has column names. I'm not going to test you on this. It's got 3 columns. Guess, revealed, and remaining. Those are the 3 things that are in our simulated values that we give back. And then you can do .append on a table, and that updates your table in place. That adds a row. It adds an entire row because we're giving all 3 values for each of the columns. And it's a little weird, but what has happened is I've just turned 10,000 plays of the Monty Hall game into a table with our guess each time, what is revealed to us, and then what we could switch to. All right. So look at how, in just like the first runs of the thing, you see car showing up a whole lot in the doors that you could switch to. Okay. Let's see here. Yeah. So here, let's look at our guess, and let's see how often we got the car. All right. Let me show you that's like a 1/3 chance. So games.group. If I group all the games by guess, it'll go through all of them and count how many times I see each of them. You see that the car, the goat, and the car in each of the goats appears about a third of the time. So that's like 3,333 is what it's supposed to be, right? If I did 10,000 of them, they're all about there. And so you see with like a third of a chance, you guess right for the car the first time with your original guess. And then the remaining column is what you could switch to. All right. So I'll call this I'll call this like original choice. And then the remaining door is this one. Let's group by that one. Dun, dun, dun. And this will show me all the ones that I could be switching to. Do you see how there's a whole lot more cars than there are these guys? That's so cool. So you should always want to switch. There's a 2/3 chance. There's about 6,666 things there. Okay, that's the ones that you could switch to. Remaining door. And so we're simulating it and proving it to ourselves. And then let me bring them together. You got your cars, your goats. Let's join them together. Remember what a join does? It brings together rows when they have things in common. I want to make a bigger table of these counts with the car goat and the other goat, and then also these counts for like if you switch, like staying counts versus switching counts. I want to therefore join this table to this table where these labels are the same, right? Car, goat 1, and goat 2. Attach the numbers in the same spots. All right. So we can start with either of the tables. So we'll say original choice. I want to join it on its guess column, because those are the ones that have that are in common with the other table. Its guess column. I want to join that with the remaining door table, and the column that has the same values that I want to join it with is the remaining column of the remaining door table. And so it's going to give me this table of counts, and it said count 2 here because it couldn't use the same name again. But I put next to the car like the number of times in our simulation that you won the car if you stayed, and here's the number of times in our simulation that you won the car if you switched. That joining brought the tables together. Okay, that's called joined. Let's say that. And then these labels on these columns look a little ugly, so let's change them. We like join dot relabeled. We can do, let's see, column number 0. Let's just call it the thing you get, like item. Oops, 0. Item. Like that, I'll call it item now. And you just keep on playing that game. Dot relabeled again. Column 1, that's the count for like if you stayed with that original door. Original door. And then the other column number 2, is the door that you could have switched to. Okay? So like that's the table now, and that's kind of what I wanted to say. So like if you stuck with your door in our simulation, you got the car that many times. If you switch to the other door, you got the car that many times. You always switched. So it's better to switch. Call that joined. It's like one big table called joined. And now we can finally make a graph out of all this. We'll say join dot, let's do a bar chart on the item, which is column 0. And this is exactly kind of what we want to see. We're proving it to ourselves, right? If you stuck with your original choice, so 1/3 chance that you got any of these, there's the same probability, right? You're not getting rid of that 1/3 at all. But if you switched, if you always switched, you're getting the car more often because of what I said here. Like you see a door with a goat, you know where it's not now. There's a 2/3 chance it was behind one of the doors you didn't guess. And one of those had a goat, and we saw that. And so now we know that there's only one out of the 2 left. And so that made a 1/3 of 2/3. Right? 2/3 chance that it was behind the other door that we didn't pick. And the rest just share like half of a third. A third over 2. This is like a 1/6 for each of these now. All right, so it's a little not very intuitive why you should play the Monty Hall game this way. I hope this explanation made a little bit of sense, but even if it didn't, you can see by the simulation where you should go, right? The way you should play the game. Isn't that weird and cool? Any questions about this weird thing? This is how we simulated the play of the game. Does that make enough sense? Definitely something to study, probably. That's what it's given back. Our original guess, random guess, the door that Monty shows back to us with a goat, and then the door that we could switch to. All right. So try to tell Google to make a random number for yourself, and then see if you got it right. Here, let's play it one last time. See if we get it right this time. I'll do it with us. 2, 3. Let's say that I pick, I don't know, door number 3. All right, so it's behind door number 1. And so Monty will therefore show me door number 2. There's a goat. And I'll be like, I want to switch to door number 1. And what do you know? That's where the car is. Cool, there's a car there and a goat there. So I won this time. All right? So it is better to switch. I hope that makes a little bit of sense. So that's what's going on. And that's kind of the reasoning. Isn't that fun? So yeah, that's a weird probabilities idea. Are there any questions about the Monty Hall game before I go on with more probability stuff? All right, just a few more things. Let's talk about, you can add probabilities in one situation. There's also a way to multiply probabilities. They mean different things. So here's when you can add probabilities and why you'd want to. So let's say you've got some dice and you want to be like, what is the probability that I roll a 2 or a 4? I think you can imagine, it's like, all right, the probability is like, these don't have anything in common with each other. So it's just like the probability of both of them added up. Right? If it's a 2 or a 4, and I don't care which one, then there's a 1/6 chance that I got a 2. There's another 1/6 chance that I got a 4. It's just it's the addition of both of them, right? A bigger probability. Just add them up. Probability of 2 versus probability of 4, and I'll have the probability of getting either of them, right? Because there's 2 options now that I care about, 2 and 4 over 6 total, so that's 2 out of 6. Does that make sense? So you can add probabilities when you want to know something or something else is true. So you want to do that with an OR. All right, so OR is when you add probabilities. And this works whenever your events that you're summing up, they don't overlap. So overlapping will ruin the day. So they did the two. You can't have a die that lands on both 2 and 4. So there's no overlap there. But let's say something else, because if they do overlap, you double count. So let's say that we want to know. Here's our dice options, right? You could roll 1, 2, 3, 4, 5, or 6. Let's say we were like, all right, I want to know if these are the 2 events I care about. I want to know if the dice, what's the probability of the dice landing on an even number, like that event, or the die landing on a number bigger than 3, one of the bigger halves of the numbers, so like between 4, 5, or 6. So those are the 2 things I care about. What's the probability that anything I circled happens when I roll my dice, right? What's the probability that either of those events takes place? If you do it naively, you didn't think about overlap, you'd be like, all right, there's for the blue step, right, there's how many options? There's 3, right? So it's 3 out of 6. There's a 1/2 chance it was the blue thing, right? Plus a 1/2 chance that it was the green thing, a 4, 5, or 6. What's the probability of getting a 4, 5, or 6? Another half, right? 50%. 3 of the options. And that's 100%. It's saying that there's a 100% chance you either get a blue number or a green number. And you see how that's wrong? The issue is because some of these numbers are in both, because we double counted. We double counted the 4 was in both of them, right? And then the 6 was in both of them. Really, the answer was supposed to be, how many of these numbers are circled right now? It's supposed to be 4 of them, right? 4 out of 6 options, right? You see how it's not the same? It's really 1, 2, 3, 4 out of those options, but we double counted some of them, and so we have to remove their double countedness. You have to take that into consideration. But if they don't overlap, you can just add their probabilities up, right? So you do have to be careful a little bit. Questions about that? It's adding probabilities when you want to. It's like an OR. Because you could also multiply probabilities. That's an AND. So that is the opposite. So multiplying probabilities is when you want to know if something and something else happens, like a succession of things. So here is the idea. Here's some examples. Like, what's the probability that you roll a heads first, if it's a coin, and then a tails next? You multiply them. So like the probability of a heads is 0.5, the probability of tails is 0.5. So it's going to be 0.25 of getting first a heads, then a tails if it's a fair coin. And the way this works, the reason you can multiply is because it's all going to branch off every time you roll a coin. Like your number of universes doubles. So here's kind of how I want you to think about it and why you can multiply. So when you flip a coin, you ask the universe to make a decision. So it's either heads, right, or tails. And there's a 0.5 probability of each of those, 50%, right? Heads or tails for your first coin flip. But then once that's happened, you're off to the next one, right? So after you roll a heads and you flip it again, you could again either get heads or tails, right? So again, you could get heads or tails, heads, tails. And if you get tails first, again, you flip it, you flip another coin, you still have 2 more options, right? You get heads again or tails. Okay, and there's a 0.5 chance probability for each of those. Right? Still a fair coin. 0.5, 0.5. So do you see how in the end, after flipping a coin for 2 times, there's 4 potential ways that you could have had things happen, right? You could either have flipped heads twice, or first heads then tails, or first tails then heads, or first tails then tails. Those are your 4 options. You see how that happened? 4 options total, and the one that we care about is apparently, I'm like, all right, heads first, then tails. So heads, then tails. I care about this one. And do you see how all the different options, there's 4 of them. I could have gotten them equally likely. So there's a 4th chance that it was heads, then heads, 1/4 chance, 1/4 chance it was heads, then tails, 1/4 chance it was tails, then heads, 1/4 it was both tails. So the way you can get there quickly, because it branches off, is all right, there's a 50% chance I got the heads first, and then If that happened, multiply that, and there's another 50% chance that I got tails after that. There's like a sequentiality kind of thing going on. So that is multiplying because you're the ways that things could happen, they branch off every time you roll and you multiply to like see that branching happen, to understand it. Okay? Questions about multiplying probabilities and why you'd want to do that. It's like one thing, then the next. I want this and this to happen, please. What are the odds? All right. So, yeah, with that, I have some questions for you. So here's my first question for you. Yeah, let's say that I've got 3 cards, because again, probability was invented because people liked gambling. So let's say I've got 3 cards. I've got the Ace of Hearts, I've got the King of Diamonds, and I've got the Queen of Spades. And I'm going to shuffle just those 3 cards, all right? So randomly, I've shuffled them. And you're not sure what's on top. Like I've got a deck of 3 cards now, those 3 in any order. I shuffle them and I take 2 cards and I'm going to take them without replacement. What I mean by that is I'm going to take 2 cards and I'm not going to rainbow because it's important. Without replacement. What that means is, let's say, like I randomly off the top, the first card I picked was the Ace of Hearts. I'm not going to the next time put the Ace of Hearts back in and maybe pick it again. Without replacement means not putting what you just picked back in. So it's impossible to get the Ace of Hearts twice. If you did it with replacement, it's possible to get the Ace of Hearts twice. Does that make sense? That's what it means to be without replacements. I'm just not putting things back in. So I shuffle the cards. I draw 2 of them at random without replacing them, so I can't get the same thing twice. My question for you is, what is the probability? What's the chance that I get the Queen followed by the King in that exact order? Does that question make sense? Try to think about that. If you're brave and willing, try to respond on our Write Nice page. Discuss it with your neighbors. And please do attendance if you've not done attendance. But try to write that down. Do you see what might need to happen there? So here, let me show you. It could be is it one of these guys? Is it that thing? That's the adding probabilities stuff. Does it need to be added? Does it need to be multiplied? Is there a weird combination of both? So let me give you both of those so that you can see them. But yeah, try to figure it out. Let me know if you have any questions and try to do it. What's the chance I get first the King, the Queen of Spades, then the King of Diamonds in that exact order? What are the odds? You have to be a little bit careful because you're not replacing. For example, with the coin flips, you can't just you're always replacing the tails, right? You're not going to be like you flip the coin and now you scratch the tails off the coin or something. So some things that we were talking about just like naturally with replacement. This is without replacement. Maybe draw a picture. I think the picture would be helpful here. You see it? Another minute to think about it. I swear the picture is the right idea. Hmm. Let's do that. Let's see. Any brave souls put an answer in? Let's take a look. Nice. We even got some work going on here. Yeah, I think we all got 1/6, and we wrote it down in different ways, and that is correct. That's awesome. I like this. Good job. Let's talk about it. It's going to be 1/6, which it's going to be an and, but it's going to be a weirder kind of and. All right? I promise to stop that. So here, let me show it to us. So it is going to be a 1/6 chance, and here's how you can kind of figure that out. So, all right, if I shuffle these cards, and I've got this deck of them, and I pick the first card, it's either the ace, the king, or the queen, right? The ace, the king, or the queen. It's like the universe splits off in that way. Boop, just like that. But then you pick again, without replacement, there is a 1/3 chance you got that queen first, right? But now, for the next card that you pick, there's only 2 cards left in your hand. You see that? It's not a third again. So if you pick the ace first, then it's either, the next one you pick is either the king or the queen. You can't like pick the ace again, right? If you pick the king first, now it's either the ace or the queen. Can't pick the king again. And same for this one. If you pick the queen first, then it's either the ace or the king that's left. You see that? You see how it's branching off? So the first time you had 3 options, and then the second time, it's 2 options of whatever's left. Okay? It is still an and, though, because of the way things are happening. So what we care about, you see how there are 6 options total at the very end, our goal. What did we want? We wanted the queen and then the king. So we wanted these guys, this one down here, and then this one right here. And the way that you can calculate, it is going to be 1/6, right? It's 1 out of 6 of these options at the end there. But the way that we can calculate that is the first time, what's the chance that you got the queen first? 1/3, 1 out of 3, right? You had those 3 options, it was random. And then what's the chance that you got the king after it? Well, there were 2 options left, so it was 1 out of 2. 1 out of 2, and that's another way to find that it was 1/6. Does that make sense? We seem to get it. Questions about that, though? So it wasn't and, but it was a weird kind of and. Okay? So that's the fun one. I have one other question now. Again, try to think about it. Again, I've got the same cards. I draw 2 cards at random without replacement. What's the chance that those 2 cards that I've picked, what are the odds that one is a king and the other is a queen? Does that make sense? What are the odds that you get the king first, then the queen, or not, sorry, no ordering. There's no ordering at all. It doesn't matter which time you got the king, if it was the first time or the second time, or the queen was your first draw or the second draw. What's the chance that you ended up with in your hand, the king and the queen, and didn't pick the ace? All right, at all. Does that question make sense? It's the odds that you got just the king and the queen. Doesn't matter the order, though. Try to do that one. And write down your answer if you'd like. I'll clear it out again. Refresh the page. Try again. But is this going to be is this like an and question? Is this an or question? I think it might be both. One is a king and the other is a queen. The 2 cards that I picked. I think a picture again would help. But do you see the underlying principles as well behind the picture? Oh, that's my timer. Did you make a picture? Do you see? What are we thinking? Any questions? Got a 2/3 chance here. Nice. Any other thoughts? Yeah, let me bring this picture back in. You press submit if you'd like. But let me, because this is still true, right? You're still drawing two cards, and like here's what's happening. But I want one king and then the other queen. You see it? So this is a bit of a harder question though. So do you see how, because the order didn't matter, if we're just going at the picture, you could have gotten the queen first and then the king, right? That's a way to get the king and the queen in your hand. Or you could have got the king first, right? And then the queen. Does that make sense? Why these two routes like get you to places you care about? Those are the two options in our total amount of options that get us somewhere we need to be. And so just like doing the math, you can see that it is a 2 out of 6 chance. Does that make sense? So that is going to be a third. 2 out of 6 chance. And a way to think of it is kind of a combination of this idea, one thing and then another thing, and then also a combination of the or. Because it's like, what's the probability? You can think about it this way. What's the probability that I got the queen first and then the king? Or the probability that I got the king first and then the queen? Do you see how those are your two options for getting what we care about here? And you can add them up because they don't overlap. And so it's as we know, right, it's a 1/6 chance to do this one. There's another 1/6 chance similarly to get this one. And so it's 2/6 or 1/3 as your final probability. So you can do the picture. You can also do a combination of ands and ors. See that? Because there was no overlap. Questions about that? Do you see it? That one's a harder one. All right. Yeah, one last thing I want to show you about from these slides is sometimes it's easier to think about the opposite. Remember that the complement is the fancy word for opposite. It's the probability that something does not happen. Just like what's the opposite is 1 minus whatever the original probability was. Sometimes it's easier to think about like, all right, what's the odds that this thing doesn't happen? It's easier to formulate your idea in that way. All right. So here's an example from your textbook of why you would want that one day. It's like, let's say you're asked like you're posed, like this question is asked to you. What's the probability that you get at least 1/6? Like you're rolling a die a bunch of times, n times. What's the probability that you roll at least 1/6 in all those? All right. That's a bit hard, right? Because it's like, all right, was the first one a 6? Maybe the second one was a 6. Maybe the first and the second were a 6. You see how all the options, like they blow up for if you're trying to do this without complements. It's like if you're rolling 5, for example, dice, you get a 6 if like the first one's a 6 or the second one's a 6 or the third one or the fourth one or the fifth one or the sixth one. There's so many options, right? Like the first one was a 6, but the second one was a 2. Maybe the third one was also a 6. There's so many different ways that it could branch off. It gets disgusting. So it's easier to think about it in terms of the complement because it's the opposite of the probability that you didn't get a 6 at all ever. Does that make sense? Probability that you got at least 1/6 is the opposite, the complement of you didn't get any 6s at all. And that one's easier to calculate. Because the odds that you didn't get a 6 at all in n rolls of a die, that's, well, what are the options for non-6s? 5 out of 6, right? 5 out of 6 options for not a 6. And you just like do that a bunch of times. Like, all right, you didn't get a 6 on the first one, and you didn't get a 6 on the second one, and you didn't get a 6 on the third one. That's exactly what you want. All right. So that's the opposite, right? So like, for example, what are the odds? Like, if it was 5 times, let's say, yeah. What are the odds you didn't get a 6 in 5 rolls? So like, that's 5/6 chance for the first roll that you didn't get a 6, and another 5/6 chance for the second roll that you didn't get a 6. And that just like, it's easy to calculate, right? If, let's say we're rolling a die 5 times. We want to know how likely is it to not get a 6. You don't roll a 6 in 5 rolls. It's that many times, right? Because for the first roll, you don't get a 6. For the second roll, you didn't get a 6. All the way to the third, the fourth, and the fifth roll, you didn't get a 6 at all. And that is 5/6 over 5, right? That's the chance that you did not get a 6, all right? And so the odds that you got at least 1 is 1 minus that. Does that make sense? The odds that you got at least 1 6. Whereas if you were trying to do this in the other way, it's like you're rolling a die 5 times. What are all the different, we have to enumerate all the different ways that you could have gotten a 6 somewhere or not, right? Be like, all right, maybe you got a 6 on the first roll and you didn't get a 6 on the other rolls. Or like I got a 6 on the second roll and I didn't get a 6 on any of the others. Or maybe I got 2 6s and maybe they were right there and right there. You see how there's millions of options? Like, it blows up super fast to try to figure this out without a complement. But with the complement, it's just like, all right, 1 minus, I didn't get any 6s at all. And the way that you ask if you didn't get any 6s at all in a certain number of rolls is that. Okay? So we can do a simulation of that, which is kind of fun. Let me show that to you. This is again an idea of multiplying probabilities. Like, I didn't get a 6 on the first roll, and the second roll, and the third roll. So let's say I would like to show all the options, show all the answers for n, where n is between 1 and 50. These are, let's try to roll a die. What's the odds that you don't get a 6 if you roll just a die once? What's the odds that you, if you get at least 1 6 if you roll a die twice? What are the odds that you get at least 1 6 if you roll a die 3 times, 4 times? So like, those are my starting numbers, then my numbers of rolls. And then I can make some results out of that. So results equals, by the way though, what are the chances that you got at least 1 6? That's it's 1 minus whatever this is, which is 5/6 to the n, all right? So I can calculate that. I can be like 1 minus 5/6, and to the power of is that, and I can do rolls. And that will just like do 5/6 to the power of each of those things, and then do 1 minus. It'll give me a bigger sequence back, just as many things. So those are my odds. Like, there's that percent chance I didn't get a 6 with 1 roll. This percent chance, this percent chance that I got at least 1 6 for the first roll is 1 6. This is the chance that I got at least a 6 somewhere with 2 rolls, at least a 6 somewhere with 3 rolls. It's more and more likely when you have more rolls. This is really hard to forget about the 6, right? So that's kind of what it's showing you. And we can turn that into a table and graph it. It's kind of cool. Equals, so give me a blank table with columns. Rolls is that, and then the chance of at least 1 6 is this. That's my chances. All right. And then that's what I calculated. It's like, all right, this is, all right, I'm rolling a die once. The chance of at least 1 6 is 1 minus 5/6 to the 1. Then this one is, all right, rolls is 2. The chance of getting at least 1 6 in 2 rolls of a die is 1 minus 5/6 squared. So it's on and on and on. As you roll more dice, right, you see that it's more and more likely to get at least 1 6 somewhere because you have so many options. Yeah. So does the formula make sense to us, at least, before I graph it? All right. So you can do a scatter plot. I guess a line plot might also make sense, but you can't really have half a roll. So let's do a scatter plot on rolls as our x-axis. And so you can kind of see this is the probability 1.0 right here. We're approaching that. Never quite reaching there, but approaching it. So the more and more times you roll the die, it's more and more likely after. It's almost perfectly likely, right? When your rolls is 50, you're so close to, it's almost a certainty that you're going to have a 6 somewhere in 50 rolls of a die. Yeah, that's because 1 minus 5/6 to the 50, like 5/6 to the 50 is such a small number. What was the 50th roll? It was like, all right, when you had 50 rolls, 1 minus 5/6 to the 50 is 0.99989. See that? So it's almost a certainty that you'll have a 6 by then, somewhere. And yeah, it's fun to graph and fun to watch the library make sense of things for us. Questions about any of that? So that's randomness. And that has brought us to the end of these slides, which is exciting. The assignment that depends on this section was homework 5. So we might as well go figure out the due date for that. And I want to just give us a little sneak peek of the next slides too, because we got just a few minutes. We'll do that very quickly. But let's see what we got coming up. I want to give you at least a week to do it. And you've got, you got a project coming up. I want to give you a lot of time to do that. So project is coming up. I want to give you enough time to also do the next assignment. Let's see. Yeah, I should be able to, just so that you don't have to be scrambling. Let's make it, so this is I wish we weren't right between months. So we got your project 1 due on the 27th. Let's do your next homework. Let's just also do that one on a Friday. Why not? So I think we can make that work. Let's do the 6th for homework 5. So you have a little bit of a break after the project. So that's that much time. Ooh. All right, so that was homework 5 stuff. And that was the end of the randomness slide. So we're going to use this stuff forever. Let me give you a little sneak peek of the next slides, and we'll go from there. I really just want to go over like one slide. We'll get there and we'll come back to it. Do I want to make a file for this yet? I don't know. I might just want to look at it. Yeah, this will be fine. So we like to run little simulations. We can do that now. And those simulations let us take pieces of a data set, right? We were taking pieces of the Titanic, for example, and so that's called sampling. We can take samples and we can come up with distributions for our samples, and we'll learn about the word empirical in that sense. So, okay, this is chapter 10 stuff. Please look into that. And I just want to kind of go over the first slide, I think. Is there anything else that I want to do here? I might show an example of this, but we'll see. So yeah, I just want to go over this slide, I think. So you're a data scientist. You want to do something. The simplest way of thinking about it is like you want to interview some people. Like you want to do a survey. That's what a lot of people like to do. So this can apply to any data that you've collected. Let's pretend you're asking somebody in a survey like who they're going to vote for president or something. So like you've got the population is the people you want to know something about, right? You want to know the likelihood of like which next president is going to win, or which like next California governor or whatever is going to win. And so your population is like all U.S. voting eligible citizens, right? All the people who are going to vote in the next election. Or your population is all the people that are going to vote in California or something like that. You can't interview all of them. And so the idea is you're always going to take a sample, right? You're going to take a smaller amount of people and you're going to see what they want, see what they're saying. and you're going to try to infer, right? You're going to try to go from here to here. You're going to try to infer ideas about the entire population that you cared about. Like, all right, if 60% of the people in this sample are going to vote for this one person, then let's predict then that that person is going to win the presidency for the whole population. And so that's one way to think about it. But there's also a way to get from here to here, right? There's the idea of like, how did I pick that small group of people that are supposed to be like telling me stuff about that giant group of people? Because you better believe that you could pick wrong. You could pick a horrible sample. You could pick if you pick nothing but college students, you probably wouldn't predict properly, right? If it was like for an election, because there's plenty of people that are like in different stages of their life, and I think you've probably heard that like people who are older tend to be more conservative because they've made their money and they want to keep it or something like that. So like that's a thing, and it's really important to get a good sample that's indicative of your population. It needs to match, right? It needs to match the way that it's going to look in real life. Otherwise, you can't infer things that are correct. All right, you'll have bad results. So yeah, let's talk about different kinds of samples that you can make. There's going to be a really good one that we're getting into, and hopefully I've foreshadowed it enough. But yeah, there are a few different kinds of samples. The first kind of sample is a very simple one. It's called a deterministic sample. It's when you take a little bit of something, and there was no chance at all. It's like, I'm taking the first 5 people that walk through this door. There was no chance at all, or maybe the people who were walking through the door that mattered. Maybe I'm going to take. Let me show it to you with a data set, maybe. Dun, dun, dun. It's called a deterministic sample. You just like, it's already been settled. There is no randomness. It's just like, you've picked who's gonna get interviewed. There is no room for choice. This is chapter 10. So let's do Pokemon. Let's do Pokemon equals. And I'd really like to only care about the Pokemon that are from Generation 1. And I want only the name, the primary type of that Pokemon, and its HP values, maybe. Let's call that Pokemon. Boop, just like that. So there's a way to, that there's a way to take a piece of this array there's a dot take. Sorry, there's a way to take a row, like a piece of this table, but with a dot take on that table. Oops. Dot. Yeah, so you have a table, you say dot take. You can give an index and it will give you that row back. So like, this is a table, this is row number 0. If you say dot take 0, it gives you that row. So like, here's my Pokemon table. If I take index 5, that's the 6th Pokemon, 0, 1, 2, 3, 4, 5, that's Charizard. So that's me taking it. You can give a bunch of indices to take, and it'll take just those, like take index, give it an array of things. Take these guys, take 0, 3, 6, and 24 Pokemon at those indices, and I've taken a piece of the table now. I've got a few rows they're at these exact indices. There was no randomness. I didn't flip any coins. I was like index 0, index 3, index 6, and index 24. Always. That's called a deterministic sample. There was no chance involved. I picked these numbers, and I'm going to keep going with those numbers. If I come back and I rerun the cell, I get the same Pokemon back. I'm taking a deterministic sample. I've chosen to only look at these 4 Pokemon, those 4 exact Pokemon. All right? That's what's going on. It's a deterministic sample. All right? You've chosen ahead of time. There is no randomness involved. There is no chance. All right? So it's like, I'm going to interview people. I'm only going to interview my family. Like, that's deterministic in that sense. There's no randomness involved. You've already chosen what's going to happen. All right? If you redid your sampling, you would get the exact same results because you're still going to interview your family again. All right? There's no difference. I'm still going to go to these exact indices. That's called a deterministic sample. And you can't really get much from that, right? Because it doesn't change. There's no chance involved. The other kind is a random sample. You can get a cool kind of random sample. So this is where we're going, right? I hope that I've motivated that, all right, a random sample is one where there is chance. All right, it doesn't have to be perfectly random, but that's kind of the best one. Before you take, there's some weird requirements for a random sample too. Before you draw your sample, you also have to know the probability of all the groups. So, for example, if we're talking about voters, it's much less likely for somebody college-aged, unfortunately, usually, to vote. So, like, if this is the group of college-age people, how often they're actually going to vote in an election versus the group of, like, 60-year-old retired people, how often they're going to vote in an election, it's higher for them, right? So when you're making your sample and you want to choose randomly and you want it to be proportional, you want to pick more old people than young people because they're going to vote more often than young people, sadly. You guys should change that. We should change that. But like that's the deal right now in the US. So like that's still random if you're picking things, but you want it to be proportional, right? So you have to know like the probability of every group in your population because not every group has equal chances of being selected. Like young people versus old people. Old people are more represented in the population of actual voters, and so they should be more represented in your sample then if you want to get a good idea of what's really going to happen for voters. Does that kind of make sense? So even though you're picking like old people randomly and young people randomly, you still want to pick more old people. So that's a random sample, and if you want it to be like unbiased, okay? So that's the idea. Yeah, there's some that aren't even. There's some samples that are neither deterministic nor random. There's like if your sample is like everybody who walks by our classroom door. That wasn't deterministic because like it depends who was here today, and then it wasn't random either because like we didn't know the probabilities up front. Like there's it's kind of the people who are here, like you know that they probably live around here. They probably either work here or they go to school here, so it's not a perfectly random set of people, right? They all are linked to Clovis in a certain way. So like that's called a sample of convenience. It's not deterministic and it's not random. It's some weird combination that's neither. So yeah, if you want to know something, sometimes you do have to do it like this to get a good accurate sample. But we care a whole lot about a what's called not just a random sample, but a uniform random sample. This is where we can do some cool math and do some fun things with. So we're going to care about that in this class. We really like random samples, but we like even more uniform random samples. Uniform random samples. That equals love for us. Okay. I need to draw a better heart. There. No. Third time's the charm. That's my best heart. Okay. So what a uniform random sample is like everybody has an equal chance. Like the probability of this person getting chosen being part of our survey, probability of this person getting chosen and being part of our survey, this person, all the way for like everybody in the US. They all have equal chances of being sampled. That's a uniform random sample. Does that kind of make sense? That's like going off the voter lists and like randomly picking people. Just perfectly randomly. It will just end up being completely... it's probably going to give you the best knowledge, right? Because it's perfectly random. There is no bias. There's no nothing at all. It's called a uniform random sample. Everybody has an equal probability of getting drawn from. Does that make sense? So that is what a uniform random sample is all about. And I think that's probably what I want to talk about. Yeah. Any questions about the difference between like deterministic and random sampling? Anything like that? So we'll come back to these words and we'll learn how to take these kinds of samples, like the cooler kinds, uniform random samples, in the next lecture. So yeah, if we're good, I think that's all that I've got for us. So I do want to talk about our test that's coming up. We've got a test that's coming up. Don't you forget. I promised it in week 9. So we are in week 7 right now. So 2 weeks. We'll have our midterm, and I will talk about that on Wednesday. Okay? So I'll do that then, and I think that's all that I wanted to record.